Welcome back. Today we're going to smash out the range of Unit 6 with any luck. You can see the project isn't really due until the end of the following week. We're here on October 9th here, and project 2 is due next week. Okay, so what we've done is you've done your tutorials, your practicals for that cover the material on project 2 last week. Today we're going to cover more in detail those theoretical aspects of that event simulator you've seen, and get you all ready to go. So you'll still have plenty of time to talk to us on Wednesday evenings, for example, and yeah, so get some help and things. Okay, so right. Does anyone have any questions or anything they want me to discuss before we begin? Yeah. All right. Okay. So just to recap, last lecture we went through how to create random numbers on a computer. This thing doesn't turn. That's weird. Oh, there we go. And how to go from a uniform random number to all sorts of distributions, like exponential and Gaussian. So right now I'm going to tell you how to calculate pi. Okay. So this is the world's slowest and most wasteful way of calculating pi, right? You don't need a computer to do this. You could get a square piece of paper and draw a circle on it, maybe with a compass or something, right? And you could throw darts at this square. And everything, sometimes you miss the square, just ignore those. But every dart that hits the square will either end on one of these blue dots, which is inside the circle. It might end on one of these red dots outside the circle. And if you look at the fraction of dots which are hits, we can see that that square has an area of 4, and that circle has an area of pi. So the chance or the probability of getting inside the circle, if it's kind of random, would be pi divided by 4. Okay, so yeah. Now, what we can do is we can get our computer to generate 2 uniform random numbers and call them x and y coordinates. Here we've scaled it between -1 and 1. And then just sort of square them and add them and check if they're less than 1. If they're less than 1 or less equal to 1, then you're inside this circle. Okay. If the distance from the origin is greater than 1, then you're outside the circle. So that's a really neat technique. Now notice that you are rejecting some 20-something% of these samples, but in practice that doesn't really matter, right? If your code's 80% as fast as some theoretical maximum, that's pretty good. So you don't need to really worry about rejection rates, which are like 80% or something. If your rejection rate is something, let's say it changes with respect to some system parameters, and in some limits, the rejection rate tends towards 1, so it's very unlikely that you accept. This can be a problem. But generally, rejection sampling is really good. Is a very popular technique because we saw above, like integrating these Gaussians and things, they relied on you actually having an analytic closed form for the inverse of the conditional cumulative distribution function. Okay, if you don't have some closed form solution for the inverse of the cumulative distribution function, or like a measure, or something that you can kind of integrate, then you're kind of stuck, right? And so there's a lot of techniques that rely on rejection sampling. A lot of the Monte Carlo techniques in physics, like for Ising models, will rely on metropolis methods and such, which are like rejection methods to target certain system configurations according to temperature and energy and things like this. Okay, so that's a really fascinating field. I've certainly been in deep with various methods which involve rejection sampling. But yeah, very, very useful tool to have. And then the final one, just to show you, is this Poisson distribution, because this will come up again anyway. So Poisson process. So the Poisson process is a statistical process where you have all these events that happen at a certain rate, but they're not correlated to each other, okay? So you might consider, say, radioactive decay. You have some sample, it has some like Avogadro's numbers worth of atoms in it, some of which are radioactive, and you end up with, say, gamma rays or alpha particles or something coming out of it. If you look at the kind of number of particles that come out per unit time, they'll come out at some relative uniform rate, but there'll be some statistical noise. Sometimes there'll be a bit more, sometimes a bit less. Okay. Now, so the Poisson process represents when you have all these uncorrelated events. You know, if if one atom or one nucleus decays, that's not going to set off another nucleus unless you're sort of in this critical regime, and then you've got bigger problems like imminent death. So generally speaking, with radiation, you're kind of imagining an atom decays and then the particles fly far away from where they started relatively quickly. Okay. So you got all these sort of independent events that are happening kind of randomly at a certain rate. And this is the Poisson process. Now you can get this in a thing. You could look at births or something, or deaths, maybe not deaths. Humans tend to be a bit violent, but maybe like the birth rate or something might follow a Poisson process. And you know, there's just a million different things. People turning up at a shop or something might be relatively different. People in the city might decide to go to a particular store independent of each other. They're not like ringing up each other. Hey, well, we'll get there at 10 a.m. You know, you don't suddenly have a million people turn up at Coles. So that's the Poisson process. So there are a couple interesting bits of statistics related to this. One is the time between events, okay? So if you listen to a Geiger counter, for example, it has a very particular sound to it where it goes click, 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 click. And the timing between two consecutive events follows the exponential distribution. So we spent a lot of time talking about the exponential distribution, and we're going to be using the exponential distribution for looking at timings between events in Poisson distributions in our event simulator in a few minutes, okay? But the Poisson distribution is when you have a process and you have all these kind of like random events, right? And you draw a box around it and you want to integrate in this kind of box, how many samples do I have, okay? So let's say this is a time-based event and the width of this box is t, and the rate of events is lambda, meaning the average distance between events is 1 on lambda, according to some kind of exponential. You know, that's given by that exponential distribution that we dealt with earlier. That's sort of like a half-lifey kind of thing. Sorry. If we do this integral, like this might be a small number, like close to 0, or it could be a number like 5 or 100 or something, but you're not always going to get like exactly 5 or exactly 100 samples in it. Sometimes you'll get a bit less or a bit more. And that distribution is given by the Poisson distribution, which looks like this one with the red bar chart here. So here we have a Poisson distribution, I believe, with a mean of 5.5. And this is what it sort of looks like. So the way we can kind of imagine or calculate the Poisson distribution is to realize that we want to look at, we're going to use this exponential distribution to generate this process, okay? Now, where I've drawn this box on the screen, I don't know if this is visible on that camera. Maybe it is towards the bottom there. The way I've drawn this box on this screen, the box doesn't overlap with one of the first events. But because we know these events are uncorrelated, we can actually just make the assumption that, okay, there was an event at the start of the box, and we're looking at how many happened after it for times t. And this is only an assumption we can make because we know the Poisson process represents independently uncorrelated events, okay? So all we do is, well, the way I think about it as a physicist is again marching forward in time and kind of using. Oh no, hang on. That's not the way it's implemented here, is it? Okay, so this is the not immediately obvious way of doing it. Okay, the way I was going to suggest is you sort of generate random exponential samples and stop once you get past here and add that up. Okay, here what we're doing is it's a kind of a rejection sampling technique. So we are starting with K is our counter for how many samples we have, right? And P is some probability measure that we have. And every time we generate a sample, okay, so this is how it is, right? So if we look at P times rand, okay, so we've got P times rand. This is representing, so rand. Oh, okay, so this, oh, I forgot the really cool way to explain this. Basically, because all these events are uncorrelated, we don't really care what K is. So what's inside this loop, in terms of the probabilities and this conditional, are independent of K, right? If there's a million things, that doesn't affect the probability of there being a millionth and one. Okay, it's just that there is a probability of terminating this loop, which you kind of eat up your good luck here. I'll have to come back to this one, the good explanation. But basically, here's another way to use Monte Carlo. Again, we're using a million. Well, this time we're using a million samples, and we're using this above algorithm to generate some counts and comparing that to the real data. Okay. So again, Monte Carlo, if you look at the sort of accuracy here, once you get enough samples, like a million samples, you can make really good distributions, right? That's good enough for practical purposes, and it only takes like a millisecond for your computer to calculate something like that. So it's pretty good. All right. Cool. So I'd like to move on to our discrete event simulator. So this is a simulation technique that we're really going to focus on in this unit. There's millions of types of simulation, but we're just going to work on this one. So when we talk about events, and if you're a physicist, this might sound familiar, an event is something that occurs at a particular instant in time and a place, probably. But we're just worried about time here. So an event happens at a point in time. It's not like an extended process that takes a few seconds to finish, right? If you have an extended process that takes some duration, you'd have an event when the process begins and a different event when the process ends, okay? So you don't tend to use a discrete event simulator to solve continuous problems like partial difference equations, fluid dynamics, this kind of thing. You use it to generate, to simulate things which are more integer-like, where you add one and subtract one and this kind of thing, okay? This thing's a bit in the way, sorry. I don't think it was there before. Okay, so when we consider a system with lots of events in it, the events are going to happen at discrete points of time, and those times can be ordered. You can have T1, T2, T3, and so on, and we could put them in an order, right? If you knew all the events after the fact, you could just sort them and put them in the order. We're going to create a method which lets us generate these events rolling forward in time, okay? And that's what your algorithm will do. So just a example, I'm going to just run through several different examples, right? Because this is a framework that will work for lots of different problems. So we're just going to smash out like 3 different problems with 3 different sets of code. And by the end of it, we're going to see what's similar about this code that we can reuse. And we're going to come up with this, and we're going to go through this event simulation engine that you would have seen in your practical last week. Okay, so let's take an example of a call center. So this is a bunch of people making telephone calls. It's probably a bit of a dated example these days because no one answers their phone when there's unknown numbers. But they're calling up people and they're trying to solicit donations for some catastrophe. And there's 5 workers and they're working for an hour. When the call is received, it goes for a mean of 7 minutes with an exponential distribution. And we'll just make some modeling assumptions here that any short calls less than 1.5 minutes is just the person telling you to go away and they don't donate any money. And that the longer a phone call goes on for, the probably more interested the person is and probably the greater amount of money they may give you, okay? So we'll have this kind of cutoff. And like, these complications and details are just here to show you how easy it is to put in any complications and details into an event simulator, okay? It doesn't rely on things being linear or simple at all, okay? So what we want to do is simulate the revenue versus time using a discrete event simulation, okay? So in this case, it is probably simple enough that we could answer a lot of the questions using analytic closed form solutions for the means and things, but we're actually going to see the individual trajectories or realizations, which are like what might happen situations, okay? So we use a few packages, distributions, random plots. You know, by this stage of the course, you should be quite comfortable just importing things and using them. We'll set the seed. This is very important because if we want to run it again, we can get the same result, okay? If we don't set the seed in your scripts, you're going to run into trouble because you're not really going to be able to reproduce what you've done. You won't be able to understand what's going on if it's going wrong or right or whatever. We've got this function that you can call and it will give you the duration of a call, okay? So it's just sampling this exponential distribution. So distributions is a package. It lets you create various distributions, normals, exponentials, but lots of different ones that might come up. It's like a toolbox. And for the distribution, you can find things like the mean or the standard deviation, but you can also sample it using rand, okay? So it's a really cool little abstraction you can get in Julia that you can just sample, create a distribution and sample it. And if you know the duration of a phone call, we can make this function of what the duration is. Now, just note for a minute, all this information about what happens in a phone call and how much money it results in is abstracted away before we even write our simulation, okay? So we can change these details and rerun the code below. Yes? So all duration, that's with defining a new function. Yeah, sorry, these are functions, yes. So both of these are functions in short form. Yeah, every time we call duration, we're calling rand, which will give a different answer. Okay, so it's not a deterministic function. Well, it's not a pure function, yeah. Okay, so simulate. Simulate is going to do all the work here. So we're going to start, we're setting up this list. We've got these 5 different callers, and they all start on a phone call simultaneously according to this distribution call duration. So notice here, so this thing, you've probably seen these comprehensions before. These let you generate an array of 5 elements because this is a range of length 5. We don't care about the index. We don't need the index number. So we just put an underscore there, which tells Julia just ignore this number. And we call duration, and that'll call that 5 different times and give you 5 different numbers, okay? Now, we create this sort of event list. In our case, our events are very simple. They're just times, okay? So the event list is a copy of this thing, which is, it's just going to be a list of times we expect a phone call to end, okay? So there's 5 times we expect a phone call to end. And we haven't made any revenue, and we start at time equals 0, and we have these logs. Now these will log X and Y for a graph, time versus revenue, okay? That's what those logs are. All right, so we just have this infinite loop while true, and we break, okay, once time gets above 60, okay? So, and we're just doing some logging. What's the final answer at that point in time? Okay, so what do we do? Given a list of events, so there's always 5 things in here because there's 5 workers. What we do is we find the index to the minimum element. So argmin, remember, is a mathematical function. You see this in pen and paper as well, which gives you sort of the key or the index or the input to a function that or a collection or an array. It'll find you the minimum element, but not the minimum element. It'll find you the index of the minimum element, and then we can use that index to grab it out. We use that index. Like this is why we use this approach, because we're using I a bit later on again. So we find the time. We check that the simulation hasn't ended. If the next thing is beyond an hour, we just stop. Okay. Now what we're going to do is we're going to record the event. So we're going to figure out how much money was made based on that duration. All right. So this is the current worker calls. Okay. And then we're going to increment the revenue by that and put that in the revenue log with a corresponding element at time t. Okay, because that's the time of the event. And we figure out a new call duration for that worker, because they're going to hang up and immediately call someone else. And we're currently at time t, so that phone call is going to end at time t plus that call duration, which we just jammed in this array here. So we can just copy it out again, add it to t, and put it in the event list. And so that's the time that worker I is going to kind of be ready to hang up, record a donation, and ring the next person. Okay. That will just continue until this break occurs, and then we return the logs. Down here, we just have a few helper functions where we're basically running multiple trajectories or epochs here, and we're going to plot them. So here we can see in 3 different colors, 3 different realizations of what might occur in this simulation. So revenue is monotonically increasing over time. But what we do see in this thing is a general feature that you'll see in every discrete event simulator. This is the core feature or the core approximation or whatever you want to call it of a discrete event simulator. There's all these plateaus, right? The changes occur discretely. This is a stepwise. These are always stepwise continuous functions. Yes, over here. Oh, sorry. Stitch time. Stitch steps. Oh, sorry. Here we're generating the 3 realizations without resetting the random number generator. Stitch steps. This thing is helping us plot. Okay, so I just talked about that this general feature of these horizontal lines. So if we look at the events, there was an event, say here, can you see where my mouse is, right on that corner? There's an event there, but the amount of revenue was constant prior to that event until the previous event. So all this stitch function is doing, instead of drawing like a line which is kind of like going up with a slope, it's creating all these plateaus, all these stepwise continuous pieces. So for each value, right? Oh, the epochs. Sorry, I did get confused. Epochs is this list of times in the time log, and values are the revenue log. Okay. So basically, this is creating like a straight line with the same epoch or time, the previous epoch and the new epoch for the x-axis, and both of them are the old value. All right, and then you get the new value at that new time, and it continues on like a staircase. Okay, so that's just a little helper function. I don't want to get bogged down in it. But so at each point in the discrete event simulation, the state is modified at these discrete points in time. Okay, you know, and you can use these kind of models for lots of things: logistics, call centers, social services, communications, businesses, ports, mining. I mean, the list just goes on. Physics simulations, if you like. this is a fun one. We've got to go here. You can create these simulations of like an ideal gas. Here we have, I believe, 2 different gases at 2 different temperatures. We open a wall between them, and they start coming to like a thermal equilibrium, and they start mixing with each other. So the red ones are becoming faster, blue ones are becoming slower, and they're becoming mixed up. And then I think you can kind of see them, and they do actually bounce off each other. So that's how this simulation works. And what's happening is you calculate the time. So while the balls aren't colliding, everything's traveling at constant velocity, right? And then when there's a collision, you can update the position of all the balls and the velocity of the 2 balls that collided. And then you keep a little list, again, with a priority queue of the balls which are next going to collide. And that's a nice little event simulator. So that's this. I actually remember during my PhD wasting some time. Don't tell my supervisor. I'm sure he doesn't care anymore. That we're creating a simulation like that and plotting it in OpenGL, and it's sort of fun. All right. So let's look at another kind of sort of real world application here, where we're looking at a health clinic. Okay, so we have a waiting room for patients. We want to sort of see how these patients are moving through this health clinic. So you have a few doctors, 2 doctors. Sorry, this is a small one. 2 doctors, and there's going to be a secretary. Where you talk to when you get there. So we can talk about the state of the system at any point in time. Okay, so if we look at any point in time, what could we be interested in? It'd be like there could be a number of people waiting in the waiting room, waiting to see a doctor. There could be somebody talking to the secretary because it takes some time to get your details. All right, and you can't serve everyone at once if they all turn up at the same time. And there might be some. So for each doctor, there might be a person with them or not. If it's quiet, nobody will be the doctors. And they could do things like go on break and other things. And similarly, the secretary, you might want to record whether they're busy or not busy, on break, that sort of stuff. Okay. So, and then there's a bunch, so that's the state. So I always think of these terms of state and events. The events that could happen is like a new person could turn up at the clinic. A person could enter the doctor's room. A person could leave the doctor room, go see the secretary. The secretary might answer a phone call. There could be different events like that, right? Now we're going to simplify this to just a few key events, but you could always enrich a simulation like this with more events to make it a bit more realistic. Okay. But generally, people in a room, it's a very continuous process. They move around fluidly, right? But we're really approximating this to mathematical model where it's really discrete events happen at instance. Okay. So let's consider the second event. So the first event was like a person. Oh, the third event, sorry. So a person enters the doctor's room, right? And then they leave the doctor's room. Okay. So what we can do in a model like this is actually schedule the event, for example, when they leave the doctor's room, when they arrive at the doctor's room. Okay. So what we're always doing in this simulation is we don't have all the events for all the future, right? We only kind of know what's going on now in the current state and what's about to happen soon. And then those processes that are happening soon, those events are happening soon, what they will do is they will spawn the next event at some future time. So if you process an event, I'm entering the doctor's room, I can then roll the random number generator, roll the dice, and figure out how long I'm going to be there talking to the doctor and schedule the event for leaving the room. Okay, because that's an event that's not going to be disrupted, or that's a process that's not going to be disrupted by other events in the simulation. I mean, perhaps it is, and perhaps you can make the model more complicated, but in this case, not. But that's the way it works, is that one event will kind of cause the next event to happen in a sense. Yes?
So when the patient, as soon as the patient goes, we know precisely.
Yes. Yeah, so when they enter the doctor's room, we determine precisely when they're going to leave. Now, whether or not that's a good model or not might depend on the thing that you're modeling, okay? But this is a very high level model. We're not going into what illness they have and what was prescribed and stuff, right? You could deep dive into that. You know, they go into the room and then they spend 5 minutes getting a diagnosis, and then that diagnosis might be something which takes more time or not. And you could break down those big sort of discrete events into lots of smaller discrete events. But still, there'll always be what's next, okay? That's step 1, diagnosis, step 2, treatment, you know? And so that's a really important part of the structure of these things. How you make them run on a computer is that you have this chain of events which trigger other events. Okay. And there's lots of general software out here that helps people write these kind of simulations. AnyLogic's one, come across a few times. And there's many others. You can use Simulink, I believe, to do it in MATLAB. I think, don't quote me on that. So let's look at another example. Okay, so like I said, I just wanted to show you that you can use these kind of simulations for many different things. It's a bit like the previous one. So let's consider a system of customers being served. Now these could be customers, patients at a doctor's clinic, you know, but there could be people lining up at Coles, right? Waiting to get served at Coles. So this is a queuing system. There might be multiple customers. There might be lots of different jobs that need to happen. Okay, and this whole idea of having these queuing systems, it has spawned like a pretty broad field because there's lots of different things in the real world which can be modeled in this way. Okay, so there's been a lot of study over this over the last 100 years or whatever. And you know you can do other maths courses like Stat 3004 and learn more about this stuff. Okay, and like I said, this is a pretty big application in logistics and these kind of applied maths domains. So let's look at a particular model that people study, which is very prototypical or whatever, called the MD1 queue. So the M and the D and the 1, they represent different facets of the system. So let's go through that. So the first letter, the M, means that people are turning up into the system with the sort of an memoryless or Markovian process, okay? So remember before I was speaking about the Poisson process, that events are uncorrelated. You don't need to remember the past in order to predict the next event. And that's a Markovian process, right? A Markovian process is one that depends only on the state now. And from the state now, I can go forward. I don't need to remember. I don't have to have a memory of what happened earlier. I just need to know a little bit of state now. And this is how like Markov chains and all these sorts of things are defined, right? In a Markov chain, you have to know the vector now, multiply it by matrix. Vector now, multiply it by matrix. You don't need to know the previous states. So that's the M. The D is deterministic. Okay, so the first process is people turning up. The D is to the queue. Sorry, people arriving in the queue. D is the time it takes to perform service. So how long does it take to serve this one person so we can move on to the next and they can leave? Okay, so in this model D, that time is deterministic. It's always 45 seconds to serve one person and 45 seconds to serve the second person, and so on. That could also be a different thing, but let's look at that. And 1 means there's a single server or a single queue. So maybe you're at Kmart and it's late and there's only one person, or maybe it's in the middle of the day. You could have a value other than 1 if there could be like 5 or 10 tellers, right? So like I said, these sort of systems have been well studied. This one is particular, there's going to be analytical closed form results for all the queuing durations, the number of people in the queue, and all sorts of things like this, okay? And people ask lots of questions. Now, the first one, when you have a queuing system like this, is the system stable? So which means if you let this system evolve over time, does it reach an equilibrium? Or does the number of people in the system queuing up start to diverge and go off to infinity? Okay, so a stable system doesn't diverge. It will tend to have finite numbers in it. And so if you want to ask a question like, what's the mean people in the queue after a long enough time? You can only answer that question if the system's stable. If it's unstable, the question doesn't make sense. It's infinity, right? So if it's stable, what is the steady state, which would mean like, what's the mean number of people in the queue? You can ask other questions about the steady state, like what's the mean waiting time? You know, if you're a person, you turn up, how long do you wait, right? Because that's what most people will kind of care about. That will be the experience that they have. You know, you might want to know the mean, the standard deviation, that kind of thing. But then there's another thing that happens is like Coles doesn't, and Kmart, they don't just stay open 24/7. The number of people don't just come at all times of day. Life's often transient, right? So the shop opens and people turn up. How long does it take till it reaches some kind of equilibrium, right? So what is the transient dynamics before it reaches equilibrium? And that can be a big thing. And so in like my field where I'm working at Alara, obviously our systems are all about transients and what's going to happen over the next week or something. Whereas other times you're solving someone's problem and you can really focus just on the steady state and how to improve the steady state. And if you can answer those questions, then you will have solved their problems, their issues. Yeah. So as I mentioned, there's kind of analytic solutions for these, especially the one where it's MM1. That's quite simple. It's like the equations are kind of linear in a sense because it's just uncorrelated events and other uncorrelated events. So the MM1 is where the serving is also an exponential, like a Poissonian process with an exponential distribution in the time. And then you can do like MM1K. So this would be like when you have a queue capacity. So if 300 people turn up at the Apple store lining up for the latest Apple Watch or whatever it is, the 301th person will just give up and go home. They won't join that queue. Okay, so it's the maximum queue length. So in each of these cases, we can come up with some sort of analytic results. One sort of important scaling factor is like, so lambda is the arrival rate, right? So the larger lambda is, the more often people come, or the 1 on lambda is the mean time between arrivals. And 1 on mu is the mean service time. So mu is the service rate, 1 on mu is the service duration, mean service duration. And you can come up with this parameter rho, and so long as rho is less than 1, the system's stable. So if on average, people are turning up to the queue at some rate, and that rate's higher than the service rate, that queue length is just going to keep growing and growing and growing over time, right? More people turning up than you can serve. So it's not stable if rho is greater than 1. Or even if it's equal to 1, the dynamics, you know, some realizations, they might just grow unboundedly. So and if you have this K, this limit, obviously the system's always bounded, right? You never have infinities. It'll just probably tend towards saturated for large rows. Okay, so let's have a look at how we might attack this with some code. We've got, again, distributions and random, and we set the seed, and we've got this simulator function, okay? And then we're going to call the simulator function with some input functions. As again, like that first one, some of the inputs to the main simulation function are actually going to be functions themselves that represent these statistical processes. If it's one of these M processes, Markovian processes, it's just going to be this Poisson distribution. It's going to be like an exponential distribution for a duration. And if it's deterministic, if it's D, then it's going to be a function that returns a constant and this kind of thing, right? So we're going to have this Q simulator. T is the total time. This is when we quit the simulation after time T, okay? So this is here while little t is less than big T, all right? So that's when that while loop will end as soon as you get past t. Arrival function. So this is the duration between the last arrival and the next arrival. And it is a function you're going to keep calling that doesn't have to be deterministic. Service function is a function which returns the duration to do service, serve the person, and they can leave. Capacity is the maximum number of people in the queue, which defaults to infinity. And initial queue size is 0. So we just start by default with an empty queue. And you can override some of these settings, okay? So what is the state of the system? The state of the system is really just the number of people in the queue. That's really the only thing that's sort of really important here. And that's what we keep track of over time. So we have an arrival function, a service function. And so at t equals 0, we figure out when does the next arrival happen. Okay, and so we call the arrival function. And then we ask the next service. If the queue starts as empty, well, there is no next service. We'll just set it to infinity, so it's not an event we worry about anytime soon. Okay. If the queue is not empty, well, we call the service function. And everywhere in here, we're going to have to look at the difference between an empty queue and a non-empty queue, because the server can't perform service if there's nobody in the queue requesting service. Okay, they'll just sit there idle. So here, let's have a look inside this loop. We keep track of the current time, previous time, or whatever, and the number of people in the queue currently. And there's two possible cases we can consider. One is the next event is going to be service, or the other possibility is the next event is going to be someone turning up. So if the next service time is less than the next arrival time, then we're going to perform service first. So let's deal with that. So the new time becomes next service, okay? The queue size decreases by 1 because they've left the queue, they've become served. So the person currently being served isn't in the queue by definition, they're somewhere else, okay? And if there's more people in the queue, we can schedule the next service by calling the service function to get the duration and scheduling it. If there's no one else in the queue, we just set that to infinity. And why do we do infinity? It's just so that this is never true, right? That's all. It's like a hack in a way. We should probably keep track of queue full, queue empty, service exists and things. And we'll see a more complicated event simulator below where that gets tracked of a bit more generically, so to speak, so you can do more powerful things. So if this is false, then the next event we're going to deal with is an arrival, okay? Notice the less than and equal. So if these are simultaneous, you let someone arrive in case the queue is empty so you can serve them immediately, okay? So that less than and equal, that less than, instead of a less than and equal, is very important there in that corner case. Again, the arrival happens, the time advances to the point of this arrival. If the queue was empty, that person should start getting served. If the queue wasn't empty, in either case, so long as the queue is not at capacity, we add the person. We add the person to the queue. Yeah. And then we unconditionally always figure out when the next arrival is, because there's always going to be another person turn up. All right. And then we got this thing called the queue integral. So what we're going to do, we're going to look at the time now, the previous time, right? And that's a duration. And we're going to multiply that by the number of people previously in the queue, okay? And we're going to sum that up. And if we look at a function like this is how you integrate a stepwise continuous function, right? You get those 2 times on those flat lines, subtract them and multiply them by the height on the y-axis. And you do that, you'll get the integral under the curve. So this thing will help us get the integral of the number of people queue over time. Okay, so what we do here at the very end, once we've reached time t, we actually divide that by t, and that will give us the mean people in the queue. So that's the integral of queue size over time divided by the total time will be the mean number of people in the queue. And we can run this simulation with various parameters. We've just chosen some here, which give reasonable looking results. You know, every minute 0.82 humans turn up. I don't understand this, but it's somehow possible. It takes 1 on 1.3 minutes to serve people. I think that's the maximum queue size is 5. We can calculate this row parameter, which is a good indicator whether it's stable or not. And we can use row in some of our closed form solutions. You would have seen this in project 2, all these rows and row primes and all these sorts of things. Row stars, sorry. And we can look at 10 million, 10 to the power 6, so 1 million, I was reading that as 10e6, 1 million time units or minutes or whatever you want to call it. Okay, so depending on the type of queue, we can come up with some closed form answers for the number of people in the queue. Here's the basic linear theory where you can see it's row divided by 1 minus row. Okay, so as row approaches 1, that really starts to diverge and go off to infinity. All right, this one's the same, it has the same behavior, but it starts to diverge a bit more rapidly. Yes, over here. Sorry, yes, this is the these are the results for the mean number of people in the queue. As you integrate over an infinite amount of time, that's sort of what that will converge towards. Yep. And then MM1K has a more complicated closed form solution. Okay. And we can run some Monte Carlo estimates using our discrete event simulator. You know, where I think T was 1 million. So injecting different functions. So here we're injecting the first one, sorry, the arrival function. So that's exponential with a rate of 1 lambda, rate of lambda. This one's the service duration. Here the service duration is deterministic instead of exponential. And here it's an MM1K queue where we've added this K parameter, which defaults infinity. And if we just run this code, we can see you can see row was about 0.63. And in the various cases, the analytic results give you those numbers. And the Monte Carlo results give you those numbers there. All right. So you can kind of see we're getting things quite accurate. The error is sort of like less than 1/1000th. Now that makes sense. We did 1 million time units. There was about an event every time unit, so it's about 1 million events. And the square root of 1 million is 1,000, and that should give you 1/1000th should be your rough, just off the cuff of the back of the envelope calculation for what your error rate would be. Now there's a lot more that goes into good error analysis on this. Like if we didn't have the analytical results, you might ask, I've got these numbers from a computer, how accurate are they? And there are methods to do that. And if you do more statistics courses and more Monte Carlo and physics and that, you'll learn those methods. Okay. So what we've done in this system is we've done a single trajectory and run it for a very, very long time. So this works for systems which are stable because there's this thing called the ergodic theorem, right? The system will always end up exploring this same space no matter where you started from. The distribution will always tend towards the same distribution. The transients will only last a small amount of time. So the longer you run this thing, the less smaller of effect the transients have, okay? So if this takes like 5 minutes to come to equilibrium and you're going for 1 million, then the error due to the transients at the start will only be 5 parts in 1 million, which is less than our statistical error, right? Or you could truncate. You could throw away the first 5 or 10 minutes worth of results to get rid of that effect. But if you're doing transient, if you're looking at transient results, you might do a different approach. You might be interested in running like 1,000 realizations for 10 minutes, right? And then doing an average over those 1,000 realizations for that initial period. Okay, so these are two very different ways of approaching the problem. And if you ask slightly different questions, you could ask very slightly different questions, and you're going to have to take one approach or the other, right? Which might affect some parts of project 2. Like, you might have to switch from one to the other, that type of thing. But just keep an eye out for what's in there. All right. Okay. We are at 5:51. We're going to take our break. What I'd love to do when I come back is to show you this, walk you through this event simulator code that you probably saw quite a lot already of in your practical. But we'll go through it. We'll see how it works. We'll see why it's designed that way. We'll see what's under the hood with the heap data structure. And we're going to see how you would create modular code and packages and things at Julia. Okay, so that's what we'll do next hour. Thanks. So just to be clear, I'll start again at 6 o'clock on the dot. Yeah, that is next Friday, right? Yeah. Okay, everyone. At 6 o'clock, we'll try and get through the rest of the content here. There's lots of more exciting stuff going on in this course, units 7 and 8 for project 3. So we'll try and get through this stuff today if we can. So the goal right now is to create a more structured event simulator that you can do more powerful things with. And on top of that, it'll be easier to write your simulations and quicker. And it will run faster than what you've seen above. Okay. So you're really getting a lot of good things out of this. So we're gonna create an abstraction. Before I talked about your simulations, they're gonna have some kind of system state, like the number of people in the queues and things like this, that you can observe the system point in time. That's the stuff you can see. And you're going to have events that occur at a time, and there's going to be a queue to store the future events that you know about. Okay. And we know that events can generate more events and edit the state, read and write to the state. Okay. So we're going to write some code that will deal with all of those things nicely for you and relatively efficiently. So we got these imports here. So we're going to use data structures that will give us this priority queue, this heap thing that we need to make the event queuing, the time-based ordering of the events fast. And we're going to create these abstract types, which we get to populate later. So we got events and state. Okay. So the system always has exactly one state, and that contains all the stuff inside of it. And there's all these different types of events in the system simulation. Okay. Now an event happens at a time, so we come up with a very concrete structure for this called timed event. It contains the details of the event that you have. This could be the queue that it relates to, or the person that it relates to, or any other kind of details. And then the time that you expect this event to occur. Okay. And we can order events based on the time that they occur. Okay. So we override this isLess function. In Julia, there's a subtle distinction between isLess and this less than operator. Okay. For most intents and purposes, the only thing it really differs in is with nan. Okay. So the isLess provides what's called a total ordering, whereas the less than operator might not provide a total ordering. If you don't know what that means, it doesn't really matter. But this is letting us override the behavior of how timed events are ordered, so that when we want to figure out which event goes first, we can figure that out nice and easily. So that's isLess is an abstraction provided by Julia. It's a part of base. Okay. We're going to have this process event function, which takes a time, the system state, and which is you can read and you can mutate, you can write to it, and the event you want to process. Okay. And this is the way, essentially, this is by creating your system state and types of events and overload this function is how you program this simulation engine, okay, as a user. Okay. So what we use this function name end syntax. This will create the function, but there's 0 methods on it. Okay. I don't know if you remember Unit 4, we're talking about functions and methods quite a lot. But this is just an abstraction. the primary reason to define it here like this is it now has documentation, and it sort of describes what it is and how to use it and how to overload it. Okay. We're going to create a few generic events that everyone can use for every simulation. One is end sim event. So when this happens, the simulation will end. This is going to be sort of built in. This is probably the only event, which is one of the only events which is really, I think it is the only event that's sort of special cased by the event simulator. Okay. So you can put this in. If you want the simulation to end at time 60, you can put this in at the beginning of the simulation, and any events that happen before 60 will get processed before it. Okay. So this is a really convenient way of ending a simulation without like having to keep track of it later. There's this log state event. So this is more for debugging. So what this will do is, you know, at different durations, you can tell it just to print line state, basically. So it will tell you the time and print line the state. Okay. Now you might notice this return empty brackets, return empty array. So this thing will not only process the event and read and write to state, it will actually return an array, which could be an empty array of new events to add to the queue, new timed events to add to the queue. So that's the time and the event to do, right? And so any of your custom events, they could spawn new events, or they could spawn end simulations. They could spawn log event, you know, they could spawn whatever they want. Okay. And they could spawn them immediately at the current time or sometime in the future. And the event simulator will get through the queue and process those automatically. So this is a nice way of writing a very decoupled kind of code. And the events simulation, the simulate function will tie it all together for you nice and easily. Okay. So this is the main deal here. Our simulation starts with some initial state. Okay. This is probably going to be mutable. Probably like a mutable struct or something like that. The init timed event. Oh, yeah. In this one, you can prime it with an event. You can tell it a time to end the simulation. So a lot of this should probably be an array, I believe, but a lot of simulations, and you might want to change that to be an array, like a vector. A lot of simulations you'll need to like initialize with a few things in the event queue, because they might be like processes like a Poisson process where you want to put the first one in and it'll generate the second one. The second one will generate the third one, but you need to like seed it with some events to begin with, and that's what that's for. So I think in the code you have for your practicals, that's probably a vector of time event, or if not, just change it yourself. You can optionally provide max time, log times, and something called callback. Okay, I'll talk about callback in just a minute. But this is, again, like the log times, this will help you with your debugging. Okay. So we start with an event queue, which is called a binary min heap. And I'm going to talk about binary min heaps and binary max heaps after this section. Okay, so today. So, but what it does is it lets you put into a heap, like a trash pile. That's what we mean by a heap. A bunch of things, and it's a min heap. So what's going to bubble up to the top of this heap is the smallest element with the event with the smallest time. Okay, and you can always just pick that off the top. You can always throw things into the heap, just treat it like a garbage pile. But the soonest event will always easily bubble up to the top. You can always just easily fetch it. Okay, and the reason we use this data structure is it's insanely fast for this kind of work. We don't have to go searching through the heap at any point. You just throw things in sometimes, you fetch off the top sometimes. It's very fast. So what we do at the beginning, we have to seed the queue with, so the priority queue or the event queue with the initial events. In this case, it's just one. In your simulation, there might be more than one. We stick in an event to end the simulation at the time provided. And if the user's provided a bunch of times for logging, we can put in all those log events, okay? So you might like log every 10 time units or something, just to get a feeling for what's going on. Yes?
That's got nothing to do with you in the
Yeah, sorry. So there's going to be a few. So this queue that I'm talking about, this priority queue or the event queue, this has nothing to do with the queues that you're modeling. These are the queues to help the simulation simulate. Okay, it's very much internal. It's not exposed like that queue. It's not returned. It just exists inside this function, and it doesn't represent the queues you're solving in project 2. It's not the queues of a queuing system. It's a bit meta, you know, you can have queues to simulate queues if you really wanted to, but yeah. The other word to keep in mind is the word heap. So in computers, there's often where you keep memories, you either keep your data on the stack or the heap. This is not the same heap as this heap. So that where the heap in that case is like when you use malloc or something in C and you allocate some RAM and you assign it to this array or something. This is what Julie's doing behind the screen. That's not this heap. This heap is synonymous with the priority queue data structure. Okay, so and we'll talk more about that. Okay, all right. So we've initialized the queue. We're going to do a deep copy of the initial state. Now, this is so that you might run one of these simulations more than once. You might want to do more than one realization, or you might want to edit some of the parameters and run it again. So inside this function, we don't trash your init state. We first copy it with deep copy, and then we work with it temporarily. Yes? Yeah, so state, it has to be a subtype of this abstract type. So you'll have like mutable state, I don't know, like queue system state, and then you'll have like is a subtype of state. And then you'll put the things you're interested in. Maybe it's a vector of queue lengths. Maybe it's a vector of the machines that are currently broken or something. You know, whatever the state is that you need to solve the problem at hand, you stick in that mutable struct, and we'll take a copy of it in the simulator, and we'll mutate that in place as we simulate, so that mutating in place makes it fast. Again, we don't have to allocate RAM to the heap. All right. So what we've got is, so that starts the simulation. Every now and again, before and after, well, before the first event and after every event, we're going to call callback. This allows you to do some user-defined code. Again, this is another alternative to those loggings. So now instead of like sampling at every, say, 10 time units, you can actually get it to print out the state after every event, for example, if you wanted it to, right? So this is an optional thing. It just defaults to a function which does nothing. But you can provide a function which, given this time and the state, does something, has some side effects, prints to the screen, or creates some data for a graph you're creating or something like that. So while true, so this is really easy. We have inserted an nsim event. So eventually we're going to pop that nsim event. Okay. So we just do while true. We're not doing while t is less than t, right? At the beginning of each loop, we get the soonest event, the timed event with the smallest time by using the pop operation. So pop means remove something from a collection and return it. We advance the time to that time. We process the event at that time using this generic function that you will have overloaded with your event type here. Okay, so you'll have provided that logic elsewhere in Julia. So Julie will know how to call this function. It will also check if it's an nsim event. If it's an nsim event, it will break the loop. And finally, this thing returns a collection of new events. Could be 0 of them, but it could be like, it could include 10 new things in the future, okay? So what we can do is we can push those things into these new timed events. We can push each one into the priority queue, okay? And that priority queue will adjust itself so that the soonest event will still bubble up to the top. So that there's a chance it becomes the soonest event, chance it's sort of after the next soonest event or current soonest event. Yes.
So this priority is basically a structure where we keep track of all of the events that we have in process.
Yeah, that's exactly what it is. It's a heap data structure that keeps track of all the events which are pending.
And then the one that's like immediately popped out is the first one.
Yeah, and when we pop one out, it's guaranteed to be the first one or the nearest soonest one. Because it won't be at this moment in time, we'll advance to the soonest event, and then we'll advance to the next soonest event. Yeah. But because it's being populated dynamically as well, we don't really know when the second newest event is until we process the first soonest. Yes.
This callback basically allows us to keep track of when actually happened.
Yeah, so callback will allow you, if you put it in, you can keep track of every microscopic detail that happened after every event. And that could be useful for debugging. So let's say there's some element of your state and you think it's going funny. You could make the events which edit that state print something. So that would be, you put print lines in process event or show or something like that in there. And similarly in your callback, you could just show those details which you think are pertinent for your debugging, right? And then just delete them later. Because that print line stuff will really slow down your simulation, like maybe by a factor of 1,000 sometimes, okay? So, computer can add floating point numbers and integers and that insanely faster than printing a few characters to your terminal, right? So just use that stuff for debugging. Right. As we said, this is generic. We can use it for project 2. I hope you do. You don't have to. You can write your own things from scratch. It's completely up to you. So here's how we might use it. So we can have one of these MM1 queues or MD1 queues, right? Like before, the service rate is slightly above the arrival rate, so it should be stable. There's a single queue, so the number of people in the queue or number of people in the system is represented by an integer. This is a mutable struct, it's a subtype of state. So that's going to be very important that you have a line of code looking like that with the fields you want inside. Now you could just use global state in Julia and fiddle with that, but that's not going to be very well encapsulated. Like we're not going to be able to deep copy it. And global state in Julia can be fiddly to work with and slower for the compiler to compile good code for. So it's much better that we keep the state in one little bundle inside this mutable struct, okay? So that's why we've structured it this way, because it's just pragmatic reasons, okay? It'll just make your life easier later, even though it's an extra hoop to jump through right now. And we're going to define 2 types of events. These events, they don't have any internal data, right? Someone turns up, someone leaves, right? They've been served. Okay, there's the 2 events. We don't need to track which queue. We don't need to track, the name of the person being served or anything like that. So we don't have to do that. In project 2, it may be important to add fields to these structs, okay? So that you can keep track of what this event is doing. This event is talking about service ending on queue number 3 or something like that, okay? This event, if you're doing individual tracking of people, you might need an ID of the person coming and going and things like this. So you can kind of like keep track of all that stuff. And similarly with the state, if you need to track individuals in the queues, you might need to not only have the state of the queues, but also the state of the individuals in there, and stuff like that. Okay, so you're going to modify this. If we process an arrival event, we're basically adding one to the, we're going to add one person to the queues. We're going to create some new events. The first event is going to be the next arrival event. Okay, so here we're creating an arrival event at some time. There should be some more spaces here, sorry, but that's okay. At some time in the future, so we're incrementing past the current time, according to the exponential distribution. Okay. Now here's a bit of a gotcha. The fact that this lambdas are global will slow down your program slightly. So in a faster simulation, you might, for example, keep parameters like this in your system state or something like that, all right? And they might not mutate during the simulation, but they're useful to keep in that little bundle. Okay, so that's just a little tip. Optional, of course, just code can always run slower if you want it to, if you're patient. And what we do is we add that event to this set of events we're returning. And if the number of events in system is now 1, because we just added 1 to it, we can add an end of service event for this person that just turned up and got served immediately. Okay, so if you turn up, the queue's empty, you served immediately, you know that in time 1 mu from now, in duration 1 mu from now, you will be served, and you can insert that into the priority queue, into the event queue immediately. And that's what we do. Finally, at end of service event, it's very simple. We just subtract 1 from the number of people in the system. We've got an assert statement here. So this is a system invariant. It's really good for debugging purposes to know things that should be true are true. So every time this function is called, we're going to just double check that this is not negative. Okay. If this becomes -1, for example, it'll immediately end. It'll immediately give you an error message, and that's a good way to check if you have any bugs. Okay. And it's pretty quick for a computer to check if a number's negative, so it's not going to like hugely slow down your program or something like that. Finally, we can schedule the next person to be served if the system isn't empty, if there's at least 1. Is that a bug? That might be a bug. Oh no, greater than equal. Sorry, greater than equal. Tricked me with the Unicode character. So if there's at least 1 person left after subtracting ourselves, we can put in the next end of service event with this deterministic time in the future. So that's very similar to this one, right? And we can simulate that, and we can get it to log at particular points of time. So we start with an empty queue. We start with an arrival happening immediately, which will spawn a second arrival and so on. And we can kind of see that over time, the queue state is evolving. Now, in this case, it's increased to 3, and then later on it's still 3, but probably in between people have come and gone. Okay. But we're going to use this callback feature so that we can log even more details and get all the events, all the time events, and we can actually plot a more comprehensive queue size versus time graph. Yes.
So is this still simulating this 1 queue?
At the moment, yes. Yes. So the reason why it's 1 queue, or part of the reason, is that we're just talking about the total number of things in the system. You know, if there were 2 queues, we'd need to keep track of 2 numbers. If there are n queues, we'd need n numbers. If you want n to be relatively dynamic, you probably want that to be in a vector, right? If you know there's always 3 queues, you could put 3 fields in the struct. But if some of project 2 talks about different numbers of queues to other parts of project 2, you know, hint, hint, nudge, nudge, you might want to use a vector or something for that kind of data. So let's have a look. we're going to do this callback function. So we're going to call this thing called recall trajectory. We've got these globals with the time and the q size. These are like those two vectors we're keeping track of earlier in that very first simulation. We're going to record for every time the current q state. So we just put the current time in this trajectory data, current q size in that data, and that's it. That's all we do. We simulate that, and these things will no longer be empty, okay? So we've just mutated these global variables. So it might be better to sort of encapsulate this a bit better, but it's perfectly fine for what we've done here. We're going to use this stitch depth thing again, so we get this little square kind of shaped curve. And we can plot it and we get a graph looks like this. So this looks like kind of like a stochastic, kind of like drunken walk kind of graph kind of thing. Because there's lots of events, so it's jumping up and down, up and down, up and down. But that's pretty cool, right? And we can run it again and we get a completely different realization. Yes. So, okay. So if I start with a certain random number c, I might get this blue curve, right? If I start, and that we call that trajectory 1, right? If I then change the c to something else and run it again, I'd get a different curve, and that would be like a different trajectory. So it's a realization or trajectory. So you think of a realization, like what if we did this for realsies, right? We sat at Coles and we counted the number of people that turned up or the number of people got served, and plotted that. That would be like a realization, you know, in the real world. This is like a simulated realization, and you can do this over and over and over again and make more and more of these curves and start taking statistical things about those curves, mean, standard deviation, stuff like that. At a point in time, plot the mean versus time, for example. The mean versus time would tend to come up and stabilize at the mean q size, unless it's an unstable system, in which case it would keep growing. All right. Okay, so instead of running a short simulation and plotting it, let's try and do a really long one. So here, our callback function is not going to be used for plotting, but for integrating. Remember, we did that, got like that integral of q size dt by basically doing some q size delta t. So we can put in these integrals again as globals. Again, probably globals aren't necessarily a great approach, but it works. And we can make our callback this thing which keeps track of the previous time or updates the previous time. So this global keyword just makes sure that in this function, when we're assigning to prev time, for example, here, it's changing this instead of creating a new variable inside this function and leaving that outside one the same, okay? So this is just defining the scope of variables that you're referring to. And again, we just difference the times and multiply it by the q size and add that to the integral. We run the simulation again. We calculate rho and the prediction for MD1 theory, and we give the two results. Here we've got relatively close, within a few percent of each other, within 2% of each other, and we've done a time of 1 million again. Okay, so that's not too bad. That's that. Are there any questions before we go on to this heap? Okay. So let's look inside this heap. It's not necessarily something we're going to like deeply assess you on or something, but it's good to know what's going on. So it's a nice little data structure. You can watch this video if you find it confusing or if you're curious. Little YouTube video is actually quite good for data structures because it can show all the data moving around. Nice little animation. So I definitely recommend looking at those if this excites you. So I sort of introduced this structure where we can push and pop things on, right? So let's talk about what the heap is. So it's a almost completely balanced binary tree. So that's a big mouthful. What's a tree? A tree is something with branches, right, and leaves. Okay, so you start with a root node, which is this one at the top, and you can branch. You can have up to 2 branches, which is the binary part. Okay, and eventually you hit the end and you get to leaf nodes, which have no children. Then you've got parents, right? You can't go down from leaf nodes, you can only go up. And from the root, you can only go down, you can't go up. Did I say that wrong? I don't know. And the fact that it's balanced means that basically all the different nodes come down to the same depth, plus or minus 1, okay? So it's roughly even. In fact, this is even more structured than that. We definitely fill in the tree layer by layer from left to right, okay? So this is some partly filled tree. You can keep adding nodes further down, but we're not going to add, for example, nodes down here until we've filled in the rest of this layer, okay? Now, each layer has 2 to the n elements in it. And you can identify each node in this tree by a little binary pattern. You know, just call the first one 1. So you always start at 1, which is the root, okay? The second one, if you've gone from the root and gone left, you encounter 1, 0. If you start at the 1 and go right, you encounter 1, 1. If you go at the root and go right and then left, you go 1, 1, 0. And this is how this number, which we've identified, these things relate to the node. Now, if you have a look very carefully, these and you remember binary, you did this in the first part of the course. You know, this looks like the binary 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, they're in order. Okay, this is a nice little pattern because that means for these trees that look like this shape, we can actually store them in a nice little array like this. And this is one of the tricks which makes these binary heaps really, really fast. So I'm going to do some Julia code for this binary heap that's not going to use this trick. We're going to keep it laid out like this, like a tree with lots of pointers to other things. But when you use data structures, you use that binary minimum heap data structure. It's using an array like this. It doesn't have to like allocate things. And it's very, very fast, extremely fast. Okay, so let's have a look how we represent a tree. So if we look at any node in here, like 101, it could have a parent. If it's the root, if it's the root node, it doesn't have a parent. It could be nothing. And it could have up to 2 children, an L child and a right child. There's a few invariants here already. If L child is nothing, then R child should also be nothing because we're filling it in from left to right. Okay, so that's a little invariant. You know, we're mathematicians. We like to have things that we know for true, like axioms or whatever, propositions, and we can use them to prove other facts of our system, right? And then at each node that exists in the tree, we have some value. In this case, for this example, I'm going to use a string. We're going to use this. We're going to put a bunch of strings in a heap, and we're going to take them out again, and they're going to come out sorted. Okay, and this is the heap sort algorithm, which I think you might have touched on with Paul. Is that right? Paul Billette. Okay, and then this thing is a little constructor. If you have a string, you can create this node. It's mutable, so you can update the nodes because we're going to move them around the tree. And then we have this tree structure, this balanced binary tree, which keeps track of the total number of nodes in the tree, which will describe the structure completely, whether you go left and right and things like that, because we fill it in a predetermined order. And it might have a root node. If it doesn't have a root node, it means it's empty, okay? So if this is 0, then that is nothing. And if it's not 0, then there's some node there. Okay, and we have a nice little constructor there to initialize it. And we can talk about things like, what's the depth of the tree? How many steps downwards do we go before we kind of run out of steps downwards? And so that depth is just a function of the number of nodes in it, okay? And we can use a logarithm power 2 to kind of determine that, because we fill in the layers 1, 2, 4, 8, 16, you know, so it's pretty straightforward. So instead of using floating point numbers here, we can use the leading zeros function. So this is a thing usually built into your CPU. If you have like a integer in binary form, like 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, this function will tell you how many zeros are in front of it, okay? And it can do that in a single cycle. So calculating things like the depth, which you might need at some points in your algorithm, can be very fast, almost instant, right? You don't actually have to go through and count up, oh, go down, or no. You know, you just know the answer. We got some code here. I'm going to skip over this code. Sorry, this is really fun code. And this prints out the tree for you. Okay, it just loops through and recursively prints out the tree. And I'll show you the output in a minute because we'll create a tree and we'll print it. And then we got this algorithm here for putting values into the tree, okay? And values here for getting things out. Now, I am not about to go through, am I going to go through this? Because we got this explanation down here. Oh, sorry. So this is, yeah, I know what this is. Okay. So what this is doing is we have this tree and it has this predefined ordering, right? So we fill it in from the top and then left to right, the next layer, left to right, the next layer, and so on and on. And this lets you put the next thing in. So you want to create a value, we stick it in a node. If it's empty, that node becomes the root node. It doesn't have any parents or children, and we're done. We can return. If there are things in it, you know, we update the tree structure to say we've inserted a node. And what we're going to do is, depending on the depth of the tree, we're going to start traversing and putting this in. So we're going to look at this bit stuff that I was talking about, the 1001 that identified a location, and we're going to use a bit mask. So a mask is like something that you AND with it, and you extract a bit. And we're going to figure out at each level of those bits, do we go left or do we go right? Do we descend to L child or we descend to R child, right? And all this while loop is doing is descending down. Do we go left? Do we go right? Do we go left? Do we right? Are we finished? Okay. So you don't need to understand this in every line of code here, but that lets you know when you've kind of gotten to it. And then pop is the same. So this will actually end up putting, so this sort of rearranges it. As we kind of descend, when you're the last one, you kind of like, you become, for example, if you're going right, then you become someone's R child, and that then becomes your parent, and then you're finished, right? And otherwise, you're just descending. And if you're the last on the left, then you become someone's L child, they become your parent, and you break, or you just descend. So that's all that is. And then it ends up in place, and you're finished. Pop's the opposite. What we do is we go down, 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 and then we remove it from the tree and return the value. Okay. So that's all this is. If there's one node in the tree, we extract the root. Otherwise, we keep descending down, down, down just before. So this is the same while true, the same mask, the same if, and the same else block. The only difference is what we do when we find our target location, is that we are removing a node here and stuff like this. Possibly, you know, yeah. So that's all that is. We don't need to go into too details, but if we put things in some order, we can see how they get stuck in. So I'm going to put in 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's no ordering here except for the order I put them in. The root becomes 1 because we put it in first, and then, you know, going left, the next thing is 2, going right, the next thing is 3, and then we go like 4, 5, 6, 7 at the next layer, and then we've partly populated the 4th layer. Okay. And that's how we put things in here. So, and then we can pop them out again. So we can pop out, and that will remove the first one. Sorry, what has pop done? Pop's slightly different to what I just said. Pop doesn't remove the last one. Pop actually removes the first one, which is odd. And then it goes and fetches the last one and puts it in the root position. Right? And the reason why we do that will become obvious in a minute, but that's just what we do in this implementation of pop. Okay. So what it's done is we've taken away this 1 in the root and we've extracted it, got its value when we popped. And what was left was 9 in the root and everything else where they were. And 9 was the last element. And it's still one of these fully left balanced binary tree shapes. Yes. Okay, so we don't want 9 to be in the root spot, but we have an algorithm with the heap, which we're going to see in just a minute, that we can fix this heap and put 9 exactly where it belongs. Okay, so this is a temporary state of affairs. I just wanted to explain what push and pop do. So push and pop by themselves put things in this particular order, and we've just chosen it, and it doesn't make sense yet, but it will make sense in a moment. Okay, so what we're going to do in a max heap, so there's min heaps and max heap. Min heaps help you find the smallest item according to some order. Max heaps help you find the biggest item according to some order. What we're going to do every time after we push or we pop, we're going to do an extra step to reorder the tree. Okay, to make sure things go in the order that you want them to go in. We introduce another layer of struct. So this is another struct that just contains that other struct, right? And this is a kind of neat thing to do in Julia. You do all the time is you sort of encapsulate something else and add changes behavior. Okay, so you do this kind of thing all the time in data structures. You wrap one thing in another thing, and it behaves different, or you tell it how to behave. And we can show it. It's exactly like how we showed the other one. Yeah. Now, dum-de-dum. So there are 2 new operations that are going to help us reorder things. We had a few invariants for our binary tree, right? We've defined the shape of it. We haven't really defined the order things are. In a max heap, there's an extra invariant. Is that if an object has a child, then the value of the child that's stored inside that node, so not these 1s and 0s, but the string or whatever, that's the data that's attached to it, should be less than the parent. Okay, so both children are less than the parent. That's an invariant. Okay, and what we're going to do is we're going to create functions that every time we push and pop, that invariant still holds true. One feature of this invariant is that the biggest element's always at the top of the tree, which is why when we popped, we wanted that. That's the one we're interested in. Okay, for a min heap, it's the soonest time event for our simulation. For a max heap, it might be the highest priority, something or other, whatever. So we have this shape, which is that tree shape, and we have this extra invariant about the ordering. Now, that doesn't mean the ordering is unique. That you could, for example, swap the left and right nodes anyway, and you'd still end up satisfying the invariant that things increase as you go upwards. And you can often swap several of the nodes around and you'd still satisfy the invariant. So there's not a unique predetermined way to do it. But this is what I would call like a partially sorted or partially ordered data structure. It's not like a fully sorted array where everything's exactly in order at all times, but we can always find the biggest thing or the smallest thing. And that's good enough. So what we're going to do, let's say we have a tree and we add an element, we have a heap and it's perfect form. It's got perfect shape. It's got the perfect ordering, and we add an element to the end using push. What we need to do is if that element at the bottom of the tree, and I should go back up here. If that element, let's say, and we put it here, if that element's bigger than this one, well, first off, if it's smaller than that one, it's in the right place and all the invariants about the ordering satisfied. So we can just leave it there, okay? If it's bigger than this element, what we do, we can just swap them, okay? We can just swap them. Unless, actually, we look at this one too. We look at this one as well. We look at both. If it's bigger than both of them, we swap them here. And if it's bigger than, no, hang on. If it's bigger than that one, it's going to be bigger than that. No, that's fine. We just swap them. We just bubble up. That's fine. It's perfectly fine. If we're bigger than this one, then we're also bigger than that one, but by fit, you know, by triangle inequality or whatever. Got to find where it was. So that's the sift up function here. So basically it's saying we start at the last node because we just pushed, right? When we push, we just put it at the very end of the tree. And then we call the sift up function, which looks at that last node and pushes it up if it needs to. And if it doesn't need to, it does nothing. This if statement's just wrong. So if you're the root node, do nothing. That's the first half. If your parent value is less than your current value, swap with them. And that's all this is. This is a swap of values, right? So you're leaving the node structure in place and you're just moving the values. And then you sift up on the parent. And you do that till you hit the root node, you're done. Finally, and we also have to have this method to find the last node, which is like always branch right, essentially. Go as right as you can. This is just that kind of like descending the tree thing. If we were doing this array-based method, all these searching methods aren't necessary. You just use binary arithmetic and you're done. It's really, really fast. And then there's the sift down method, which goes with pop. So what we do with pop is we take the biggest element from the top of the max heap and we put something from the end of the queue, we jam it up there. Now we know that this is going to be wrong, right? Because we just took something from very far down low in the tree and put it on the top. So that's not going to be the second biggest element because it's not even one of the two near the top, right? So what we have to do is start sifting this thing down and bubbling it down until it's in a bad spot. So there are a few different cases. If there's no children, then we can leave it there, right? Maybe there's only one thing left. That's fine. If there's only a left child, we need to check whether we're bigger than it or not. If we are bigger than it, we're fine. If we're not bigger than it, if we're smaller than it, we should swap with it. And then recursively call ourselves until we keep going down. If there's a left and a right child, we need to check both. That's fine. That's nothing particularly hard about that. And that's sifting down. So what we can do is we can take like a max heap. We can put a bunch of strings in it. Here are some prime ministers, sort of, and we can put them in the heap. Okay, and we can look at the heap, and then we can print them in reverse order by just popping them off. Okay, because it's the max heap. It'll give you the biggest string in alphabetical order. A is the smallest letter. Z is the biggest letter. Okay. So we end up with Gough Whitlam here at the top of the tree, but everyone else is in a kind of randomish order, like Turnbull's here before McEwen, if you just look at the pure tree ordering. But that doesn't matter because both T and M is less than W. Okay. And if we just extract them all one at a time, we always get sort of reverse alphabetical order there. Okay, that's that. That was probably a lot of detail about trees. Now, I've given you a bunch of code. I'm just going to go through modules, and we'll go through hopefully packages a little bit next lecture, because this won't take very long. Or if it does take a few minutes, I'll just pause and we'll continue next time. So that was great. That was a binary tree. It had a generic type parameter for the value you put in it. But we can make it a bit more modular and stick that in its own piece of code so that other people can load it, or you can load it in your different projects. So what is a module in Julia? A module is just a namespace, okay? So modules are different to files in Julia. So a file can contain more than one module in it, or a single module could be split across multiple files in Julia. Both of those are fine. In some programming languages, they're tied together, okay, but not in Julia. But what they do is they provide a namespace. The global variables and the functions and the types in that module, they live inside that module. They don't like live in base. They don't live in everywhere else, right? Yes. So, yes. So yes. So in Julia, the using keyword can do two things. So there's using will always load a module for sure and import it and let you use that module. Also, if the module has exports, it will provide you those exports. But also using, if the module happens to also be a package, it will do some additional steps to find the files where that module exists and load them. Whereas if you have a module in your current file, you don't need a package manager. It's just there and you can just using it, right? Yeah. So a module looks like this. It has a module name and end thing, sort of like structs do and functions do and all that. And everything in between lives inside the module. And that module, like I said, it's a namespace that can have variables and things in it, okay? So if we look at Julia, there's three modules built, core, three modules built into it. Base is the one where it has like print line, right? This is the one that defines all that. Core has the compiler, and main is the one where the REPL starts. Okay, so every time you start a new REPL, you get a new main that's fresh and empty. But you know, I haven't defined why, for example, main, so it doesn't exist. Okay, so there are modules, and every module sort of has its own names, and you can import names from other modules into you, and you can use the export keyword to export them so that other people can access them easily. Okay, and so, but it's just a way of organizing your code in a logical fashion, which the compiler can deal with identifying. When you said X, you meant that X, not that X, right? Just like the scoping rules, you know, it's just another layer of organization. To make like a modular max heap, what I can do is I can create this module called max heaps. You know, if it's a data structure, you usually just add an S to the name there. You can add documentation there. And I'm just literally taking all that code we had earlier and I've just copied and pasted it all here. That's all that is. There's no line of code here, which we haven't gone through today. Okay. So which is why I'm not going to like go into detail, but you can access these notes online and just have a look. Right. And then we can have this max heaps algorithm thing. This module overrides, like, for example, show inside base, and it will export, I believe it will export something, exports max heap. All right. So we have all these different types and functions in here, but when you are using it, you don't see all that stuff. It's sort of invisible. You just get max heap. And then you call the functions on base with it from base, which you probably already have imported. And away you go. And it's just a way to organize things. Next lecture, tomorrow, I will go through a little bit about how to work with files and packages briefly. And hopefully that will give you enough grounding for project 2 and project 3 in terms of organizing your projects. But again, reach out to me and the tutors and things if you have trouble with that stuff. Sorry for going a few minutes over, but we're done. Are there any questions? Anyone have any burning? Yeah, no worries.